Hi, this video finishes Unit 9 with Binomial Theorem and Pascal's Triangle. Calculus will revisit the link between the two. Binomial Theorem can be used in calculus to prove the power rule, which is a common way in Unit 2 to take derivatives, which is very important in the course. Down the road, Binomial Theorem can be a creative way to solve problems from complex roots to probability. So let's find some patterns that are good shortcuts when we want some or all of the terms when you multiply binomials. First, we have a column for raising the binomial a plus b to increasing powers. You can see there. The large middle column will be the result of multiplying the binomials, and we can fill in the final column with the number of terms in those expansions. We can pick up the pattern and see the number of terms is always going to be one greater than the power of the binomial in the first column. So you've got one term here when the binomial's power is 0, two terms when it's 1, and we might as well go ahead and do that. Okay. So for the middle column there, anything to the 0 power is 1, and anything to the first power is itself, so those aren't surprising. You've seen row 3 before. Remember, a plus b times itself has a middle term. It's easy to think that's a squared plus b squared, but it's, of course, if you FOIL this, you're going to get 2ab. Don't forget that middle term, and we will get tired quickly of seeing all these extra terms. A plus b to the third power is the previous answer times another a plus b. So, might want to erase that, make it a little nicer here. We could do this and do this the long way, and that's the entire point, because we really don't want to. You could distribute the a to a squared 2ab and b squared and the b, and keep doing this, and we'll get even more tired of seeing those sort of things. It's going to get a little painful very quickly if it hasn't already here. So let's see if we can find a shortcut for that kind of thing, and that's what Pascal's Triangle is all about, the array of numbers in the upper right here. So Pascal was a child prodigy, lived a long time ago. Did most of his work at an early age. He did help influence what eventually became calculus. You can blame him in part. So, you can imagine a young Pascal, lazy summer day of dank memes and Fortnite. He gets a text, HMU, calls, what's good? Young woman said, I just got Netflix. And before she can finish her thought, Pascal said, what I'd really rather do? I'd like to add up numbers in a triangle as a shortcut to do a binomial expansion to a large power. Yeah, unsurprisingly, Pascal died alone. Okay, so you got a triangle with ones down the left as you look towards the bottom of the triangle. We've got ones, and this pattern will go forever. Ones down the right, same with the right side. And then all the other entries, each entry is just the sum of the two numbers right above it. So there's a 2 because it's the sum of the 1 and the 1 right above it, and 1 plus 2 is 3, and 2 plus 1 is 3, and so on. And you could do this forever and ever. And so, for example, the next two lines would be, in addition to the 1s that you always start and end the row with, 1 plus 5, 5 plus 10, 10 plus 10, 10 plus 5. You can see the symmetry that's going on there. You've got, if you have an odd number of terms, you're going to have a middle number, and the symmetry, 1, 6, 15, and then 15, 6, 1, backwards, headed the other way. And if you have an even number of terms, like in the next row, you're going to have a couple of 35s as you add the two numbers above it. And the same symmetry is reflected there. So, you might have noticed the first few rows of the triangle correspond exactly to the coefficients in the middle column of binomial expansions. For example, 1, 3, 3, 1. That looks like the coefficients for 1, 3, 3, 1, a plus b to the third power there. And so on. And so this is going to give us a reasonable shortcut for doing problems like this here. And I'm going to pause here for a moment with a little magic then. We're going to write some patterns that we've found down at the bottom of the screen. Bam! For each polynomial, it says on number 1, describe the pattern for the exponents on A. They're just trying to get you to think about the pattern here. What's the largest exponent? What happens to the power? So the first term of each expansion is A raised to the power of the binomial, whatever the exponent is there. Then the exponent on A decreases by 1 in each term until it's A to the 0 in the final term, which you usually don't write. So for example, on A plus B to the 4th, A to the 4th, then you find A to the 3rd, A to the 2nd, A to the 1st, and you're not going to write the 1, and you're really not going to write, in most circumstances, A to the 0 power, which is anything to the 0 power is 1, and 1 times B to the 4th here is going to disappear. Now for the second one, they're trying to get you to think about the exponents on B. You can imagine they do the opposite, as you may well have already noticed. The exponents on B are going to start with B to the 0, even though you're not, again, going to see this. And then B to the 1st, which you won't write, B to the 2nd, B to the 3rd, B to the 4th. So if the exponent's 1, we can ignore it. And that's going to set our pattern here for what happens to the A's and the B's. B, by the way, could be negative. We'll deal with that later. And the coefficients in front of that, the 1, the 4, the 6, the 4, and the 1, 5 terms. I've got the 5-term row in Pascal's triangle, and unless A or B has either one or both, might have a coefficient or be just a constant, which certainly does happen and will happen on the back of the sheet. Absent that, you will have 1, 4, 6, 4, 1 as the coefficients for the problems here. The expansion of A plus B to the 4th. Let's look at the final two, which will help us directly and indirectly with some of the problems on the back. Find the sum of the powers for each term. It so happens that each term's exponents in an expansion equals the exponent on the binomial. In other words, A to the 4th, that's all I've got, so that 4 has a degree of 4. 4A to the 3rd, B to the 1st. So you have 3 A's, you have 1 B, there's another 4. And again, the coefficients, they're included in here, including the signs, which isn't going into what the degree is. 2 and 2, 1 and 3, 4. So every term of A plus B to the 4th has in its expansion a term of degree 4. And so that's going to help us take a big shortcut here later on. The final one, how many terms are in the expansion for each row? It's 1 greater than the power of the binomial. And so this is 5 terms, as we've noticed, matching up with an exponent of 4. 6 terms matching up with an exponent of 5. That's going to help us here in a bit also. So between Pascal's triangle and those patterns, we can multiply this with a great shortcut instead of having to do this the long way through a bunch of unnecessary multiplication. So hey, Pascal gets the last laugh. He said, I got my name on a triangle, dude. What do you got? And you said, hey, wait a minute, where's Binomial Theorem? I thought this was called Binomial Theorem. You're right. So as we flip over to the back side, the Binomial Theorem will give us a similar structure to find the terms for these binomial expansions, including a second and somewhat familiar method to find the coefficients in particular. So on the back, we have an area at the top saying binomial coefficient, and one below showing the full binomial theorem. Look at the theorem here for just a moment. The first few terms there show you a familiar structure for the A values with decreasing exponents, the B values with increasing exponents, and then something in place of the Pascal's triangle coefficients. Now look back up to the top where it says binomial coefficient again. You may remember either the notation that looks like parentheses or the one that has these exclamation point looking things here. Remember factorials? These are combinations from probability. Now, why did combinations, of all things, rear its very ugly head here? It's worth understanding why for just a minute. So here's the defense of why. Let's say I have A plus B times A plus B times A plus B. We looked at that on the front. And we know how that's going to turn out. It's going to be, so we might as well get this in here. A to the 3rd plus 3A squared, and here comes a B, and then another 3 for the coefficient, A, B squared, B to the 3rd. So if you multiplied that out the long way, that's where you're going to end up. Now, I could ask, in how many ways could I pick one of the two terms from each binomial? So here's one, here's one, here's one. So I'm going to pick one of the two terms from each of them. And if the order doesn't matter, which it doesn't, and that's why we're doing combinations instead of permutations, there's only one way I can go through and pick a group of all three A's. I can pick an A out of this one, A out of the second one, A out of the third one. That's it. And for that matter, it's the same for the B's. So I only have one A to the third term and one B to the third term. But there are three ways I could make the A squared times B term. You know, I could take an A out of this one, an A out of this one, and a B from the third one. Or maybe I could take the B from the middle one and a couple of A's. Or, you know, maybe I could take the B from the very first one and a couple other A's. And so there are three ways when you're combining through multiplication that is going to happen when you multiply it out the long way. And so if you think of the three as actually a combination, when you do the binomial expansions, the main idea is the coefficient of each term is really just a combinations problem. If you find this easy to do the non-calculator way that I'm going to show you, you might skip ahead a couple minutes here in the video. This notation, this n choose j is one way to say it. That's a way it's pretty common. Some people say n items taken j at a time. In the first example at the top here for binomial coefficient, the top number 6 is the n, and the 2 will be the j. So to set up the fraction to calculate these, we take the top number, and we're going to put a little exclamation point after it, but we'll call it factorial. Factorial means start with 6 and count down to 1. In other words, 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. And obviously the times 1 won't change the calculation. To finish setting up the fraction, we put 2 factorials in the denominator. So the bottom number, which is 2 in this case, that's going to go right in here. And then you take 6 minus 2, the top number minus the bottom number, and I get 4, and that number also makes the denominator of the fraction. Now, you can use this, you should use this structure every time if you're going to do this the long way. Now, to simplify, you don't need to multiply all the numbers and then try to cancel them. And you don't even need to write out all the factors and cancel them, really. Only write out the numerator until you reach the larger number in the denominator. In other words, 6 times 5 times, I could write what I wrote just above this, but I'm going to stop at 4 factorial because that matches the larger number in the denominator, and I can cancel those because whether you write them out the long way or not, they have the same numbers, and they're going to cancel right away. The 2 factorial is just 2 times 1, which is just 2, so technically you can get rid of this, and if you cancel 2 with the 6, all I have left, and you have to be careful when you're canceling, 3 times 5 is 15. Don't miss any of the factors there, but that's how you do a factorial. Let's do another one here quickly. Again, if you're okay with this, you might skip ahead a minute. 9 factorial, the top number, the bottom number, 3 factorial. Because it's a combination, I'm going to do top number minus bottom number. And so if I wrote this out just enough to cancel it with the 6 factorial in the denominator, 3 factorial is 3 times 2 times 1. I won't write the times 1 since that doesn't really matter. 3 cancels with 9, 2 cancels with this. There are obviously ways to do this on the calculator, which we'll need here in a minute anyway. 3 times 4 times 7 is 84. Okay. When you have 4 choose 4, or for that matter, 4 choose 0, from the earlier discussion, there's only one way to choose a combination of 4 things out of 4. So if I'm with 4 of you in a room and I want to send all 4 of you to the office to pick up some things for class, there's only one way to do that, since the order you walk out the door doesn't matter in that example. This also explains the strange temporary result in the fraction here, since 4 factorial over 4 factorial is going to top number, bottom number, and then 4 minus 4 is 0 factorial. Now, the defense of what I'm about to say is the fact that, like I said, we know this answer is going to equal 1, and so if you cancel the 4 factorials, 1 divided by something is 1. The only way for that something to make that a valid equation is if 0 factorial is defined as 1. So again, the answer is 1 here, but whenever you come across 0 factorial, we're going to define that as 1. 1 factorial also is 1. And so don't let that be 0 and think it's going to multiply everything by 0 and suddenly make this nothing here. So the final one, you'll want the calculator. So 30 choose 12 is 30 factorial over 12 factorial. Again, if this were a permutations problem, there'd be no second number here. This is 30 minus 12. There's not enough that cancels to make this multiplication humane. So to avoid a lot of painful calculation, we've got 225. Okay, 86,493,225. The binomial theorem shows the structure to find terms for binomial expansions like we did on the front side, and now we use combinations to find the coefficients. You can always use Pascal's triangle to find those same coefficients, but combinations is an increasingly efficient method as the exponent on the binomial increases. So it's worth writing out what a and b, the two terms of the binomial, each equal, and what n, the exponent of the binomial, equals. Might as well start with n, since that sets up the first coefficient and first exponent in the expansion. So for x plus 3 to the 5th power, n is 5. The a term, the first one, is x, and the b term, positive 3. The b term can be negative. We'll find an example of that later. We can look right above to the binomial theorem for our structure. The first coefficient is n choose 0. N is the exponent, which is 5 here. So we're going to start off with 5 choose 0. We know that's going to turn into 1. And you can go through and do all the coefficients first. You can then go back and do all the powers of a first, and then all the powers of b. Whatever your system is, you find something that works for you as you go through these problems, whatever you think is faster. I'm going to set up the full first term first. So 5 choose 0. The a term is x, and it's the full 5th power, just like the power of the binomial here, so that gives us our first exponent. And b is a 3. Now I'm going to write this for the moment. It's 3, and whatever that is to the 0 power, even if it's a negative number, it's going to turn into 1, and times 1 disappears from the problem. So I'll set it up that way, and then cross it off. Now you may decide to leave that in there without crossing it off. I'm going to leave it in there just enough to give us a hint about setting up the next term if you look above it. So again, 5 is the top number because in this problem the exponent's 5. It's going to be the top number in all of the combinations as we go left to right here. And we're going to keep increasing the second number by 1. So we're going to choose 1. And now I've got x to the, we're decreasing by 1 like we did on the front. And now times 3, which is the b term. And that's going to stay in there for the moment. We'll just leave that there to the first power. Now, personally, I like Pascal's triangle for exponents that aren't very large and combinations for exponents that are larger. But you do, again, what works for you, and just be ready to do either. Plus 5 choose 2. X is decreasing. B, which is 3, is increasing by 1. And again, we're just going to follow this pattern as x continues to decrease and b continues to increase until we get times 3 to the 4th. And the final term, once you get 5, choose 5. Once you have the full number there, you are finished. I'll go ahead and write in x to the 0 power this time just to keep the pattern going, and 3 to the 5th. Okay, so just for the sake of time, we're not going to go through and re-simplify all of the coefficients here in terms of the long way, calculation-wise. You'll also notice a pattern. It should be exactly what you would expect from Pascal's triangle, and exactly what you would expect from the examples above here. So 5 choose 0 turns out to be 1. 1 times x to the 5th, of course, times that 1. Let's play along with that for this time. 5 choose 1 is 5. X to the 4th, and then times 3 to the first power. 5 choose 2 is going to be 10 times x to the third times 9. This is why the final coefficients will be different than Pascal's triangle. We'll start by including them with the combinations parts here, where we're going to get our 1, 5, 10, 10, 5, 1. But as we go through, we're going to be multiplying by some power of 3, which is going to change our answer a little bit. 3 cubed, 27. Make sure you don't make the careless mistake there, and make sure you raise the powers appropriately. 3 to the fourth, 81, right? And 5 choose 5, just like 5 choose 0. That's going to result in 1. So does x to the 0. 3 to the fifth is 243. Okay. So this will look similar to the problems on the front, except you don't have a second variable with an exponent. That b term turned out to be a coefficient, or a constant in this case, and is going to be part of the coefficient of the final answer. So the full expansion here, as we simplify, so again, the second term, it's 5 times 3, do the part that you can there. 10 times 9 for the coefficient of the cubic term here. 10 times 27, 270, x squared. 5 times 81, give me 405x, and then don't forget about the constant term. We're done with x's, but we're not done with the b term. 3 to the fifth, 243. So some combination of the patterns of starting with x to the fifth, since this was the entire binomial raised to the fifth power, and working your way down, decreasing the x's, starting with the b term, whatever that is, which was 3 here, and increasing the exponents by 1. And then the coefficients, either through binomial theorem, from using combinations, or from Pascal's triangle. As you're doing these problems on your own, you can decide for any particular problem, and you should, which one's easier, and do the one that's more efficient. Let's try the second one. The coefficients for this one are going to end up the same way as Pascal's triangle would make you think, but because of the exponents here, as I go through and am deciding what n equals, n is 4, a is x squared, so each term turns out in this problem already has an exponent, so the exponents will look different as opposed to the coefficients looking different in the previous example as compared to the Pascal's triangle row. And let's go ahead and start. So we, again, can refer to the binomial theorem. You start with the exponent on the binomial. We're going to start with 4 choose 0. That's what the formula tells us. And I'll do it this way this time here. I'm going to skip through. Now again, you're going to decide what you like. Sometimes I find this faster. You can choose to do it or not to do it. If 4 choose 0 all the way to 4 choose 4, it's going to structure the problem here for us. In fact, we'll be adding all the way through. And then the first term here, I've got x squared is what's being raised to the fourth power. Remember, that's when you're going to multiply exponents. So you're going to end up with x to the 8th for that first term. The b term, y squared, or anything else to the 0 power, I'm just going to put a little mark there just to remind me that, yeah, I didn't overlook that, but it's times 1, and who cares? So we'll move on from that one. Okay, so the x squared term, so that's what I'm going to introduce every time, but it's to the third power, and then it's going to be to the second power, and then x squared to the first power, and then x squared to the 0 power is not going to show up over there. And then how about y squared? So y squared gets introduced here for the first time to the first power, y squared to the second, y squared to the third, and y squared to the fourth power here. So again, make sure you're multiplying exponents appropriately, and just being careful to make sure your factorial problems, as you do 4 choose 0, and as you go across, Those are, again, going to match your Pascal's coefficients, and so the numbers in the appropriate row of Pascal's triangle. So 4 choose 0 is 1 times x to the 8th. So that's going to be my entire first term. 4 choose 1 is 4. X to the 6th, y to the 2nd. Then I've got 4 choose 2. That's going to be 6. Remember, it's 4 factorial over 2 factorial times 2 factorial. Both of those 2 factorials in the denominator. And each of those have values of 2. So 6 x to the 4th, y to the 4th. And 4 choose 3. Again, the pattern from before. 4 x squared, now y to the 6th. And 4 choose 4 is 1. X squared to the 0 power is 1. So all those things multiplied to y to the 8th. And we're finished with that one. X to the 8th, 4x to the 6th y squared, plus 6x to the 4th y to the 4th, plus 4x squared y to the 6th, plus y to the 8th. So again, the coefficients match what you would have expected from Pascal's triangle. But in this case, because we started with terms that each had a squared in them, you can't automatically populate a full answer just like it's plain old a plus b, which are each have coefficients and exponents of 1. And so those are the simplest examples that do follow the pattern that's on the front side. And the last one of these full examples, and not a moment too soon. Oh boy. All right, n of 3. A is 3m, and b is, careful, negative 2p. So you could rewrite this as 3m plus, again to stay with the structure of the binomial theorem, and the second term be negative 2p in this case. So, again, this is a case where you may follow the original coefficients from the front. This is only to the 3rd power, and so, 1331 is not a shock that's how that's going to turn out for the, at least starting with the coefficients, but with this a term having a number of 3 and b having also having a coefficient here of negative 2, it's going to be a little more unpredictable as to what the final answer will be. So I'll start with, again, power on the binomial that sets the top number. Always start with 0 as the bottom number, and we'll increase by 1 as we go across. It's not as easy to write in a bunch of pluses here, so we'll hold off on that for a minute because of that negative. 3m is the a term to the 3rd power. All right. And don't remember, 3 to the 3rd is going to be 27, not 9. And yeah, the 3 is included in since it's in parentheses, since that's part of the a term. The entire a term is raised to the 3rd power. That full monomial is raised to the 3rd power. So make sure you appropriately raise that one to 27 here eventually. And then negative 2p to the 0 power, again, anything to the 0 power is 1. So I'm going to put a plus here for a minute, but as I do 3m squared, and now the second term, negative 2p to the 1st power. I'll just have to keep an eye on that negative here. 3 choose 2 is the coefficient, at least for the moment. 3m to the 1st power, negative 2p squared. Negative is going to disappear in that case. And then not in the next case, where 3m to the 0 power, and then negative 2p to the 3rd power. Okay. So I've got 27m to the 3rd. I have 3, let's be careful, 3 choose 1 produces a 3, 9m squared. I'm squaring both the 3 and the m. And now times a negative 2p. So we'll sit there with that for a minute. 3 choose 2, same thing as 3 choose 1, because the two numbers in the denominator end up being the same. Both 1 factorial and 2 factorial. That's why you see the symmetry in the combinations problems. 3 times 3m times positive 4p squared. And then 3 choose 3 is 1. So is 3m to the 0 power. And then I've got negative 8. Remember, negative 2 times negative 2 times negative 2. So don't say it's negative 6. It's simple to do sometimes, but Hard to carry out. P to the third power. Okay, so let's just make sure we get the final signs and multiplications squared away here. 3 times 9 times negative 2. This should give us negative 54. And I'll keep the m's going here. Keep some nice symmetry in the answers. 3 times 3 times 4 is 36. MP squared minus, no reason to say plus negative. Might as well just make this as, save a sign here. Save the environment. Negative 8p to the third power. So there we go with the expansion of 3m minus 2p to the third power. Now what if you wanted to find only a particular term in one of these expansions? Come on, you know you're curious to find, say, the 7th term in the expansion of 2x to the third to the plus 3 to the 10th power. It's okay, you don't have to admit it. You could start writing out the terms till you reach the 7th term, counting left to right, and set up and simplify that term. You could. Let's look for something a little faster. Let's write out what we know, the usual n equals, a equals, b equals stuff. N equals 10, right? A is 2x, b is positive 3 here. And so what's the final answer going to look like? I mean, we could write out that much. We know something. We know that if we wrote this out, it's going to be 10 choose something. Is that fair? I mean, that's the original exponent on the problem. The a term is going to be 2x to some power that I don't know yet. And then times 3 to some power that I don't know yet. But that's, you know, that's a good start, right? Let's look at the previous problem for a pattern you'll find on all these problems, and maybe you've already noticed. So if you've got term 1 here, so here's term 1 written out the long way in the previous problem. So I'm looking at 3m minus 2p just to pick up a pattern here. Term 1 is choose 0, and the exponent over here on b, which I didn't write, you know, the negative 2p, is also 0. And so here's the second term, and that's choose 1 and exponent's 1. I don't mean to circle that as if it's a 0. Make it look like a 0. That's a 1, and so I'm drawing your attention to that exponent. Here's the third term, choose 2, and the exponent on the b is a 2, and the fourth term is a bottom number, and the combination there is 3, and the exponent's a 3. Can you see why that might be interesting if I want to know the 7th term? If it's the 7th term, the term number, in particular here, 7, remember this term number, 4, is 1 more than these two numbers. The term number 3 is 1 more than these two numbers, and so on. If I have the 7th term, the bottom number in the combination is going to be a 6. It's going to be a match for this number. And from the front side, they told me that everything, in this case to the 10th power, for example, that the degree of the term is also going to be 10. In other words, just add the exponents and get 10. This has got to be a 4 if these two exponents, 4 plus 6, are going to equal the power on the original binomial. So 10 choose 6, we'll save a bit of time, that's 210. 2x to the 4th, remember the 2 is also raised to that power, and 3 to the 6th is 729. So with a big nod to the calculator, final term, rather substantial, well over 2 million. Don't forget the x to the 4th because they wanted the full term. So in the last one, they've gone so far as to say 12th power, so 12 choose something. Again, 3x is going to be the first term to some power times negative 1. Just depending on this exponent, could change things. But wait a minute, they told us they want the coefficient of x to the 4th. Okay, well if that's a 4, what does this number have to be? If the sum of the exponents equals the 12, 8, which is a match automatically for that number. Alright, it's 12 choose 8 times 3 to the 4th, which is 81, times positive 1. 40,000. 95. All right. So, got it in the right way. So, big ups to the big man in the office, Johnny D. Shout out to 4th Block Pre-Calc. Play on. Much love to my girl J.O.B. repping NY. Staten Island Hustle. See ya.